External flow, drag, and lift. This chapter discusses external flow that occurs when a fluid moves over objects, such as cylinders, spheres, or wings. The main focus is on understanding drag and lift forces generated by the interaction between the fluid and the object surface. These concepts are essential in mechanical engineering, especially for vehicles, aircraft, and wind-exposed structures. The discussion links physical phenomena with flow models and measurable forces. The entire analysis forms the foundation for efficient aerodynamic design. Learning outcome. The learning outcomes emphasize an intuitive understanding of physical phenomena in external flow, such as drag, lift, and flow separation. Students are expected to be able to calculate drag forces for common geometries. The effect of flow regime on drag coefficients for cylinders and spheres is also a key focus. The fundamentals of flow over airfoils and the calculation of lift and drag forces are included as well. All of these aim to equip students with strong analytical and practical skills. Wake vortices behind aircraft. This figure shows the formation of wake vortices behind an aircraft due to airflow around the wingtips. These vortices rotate in opposite directions and can persist far downstream. Their presence can disturb surrounding air or clouds and can be hazardous to other aircraft. This phenomenon shows that external flow not only affects forces on the object, but also the flow field behind it. This concept is very important for flight safety and airport aerodynamics. Aerodynamics in nature and technology. This slide shows that aerodynamic principles apply both in technology and in nature. Aircraft use lift and drag forces to fly efficiently and stably. Wind turbines use aerodynamic forces to convert wind energy into mechanical energy. Birds demonstrate that evolution has produced shapes that are highly aerodynamically efficient. All these examples emphasize the importance of understanding the interaction between flow and object shape. Flow dynamics, 2D, axisymmetric, and 3D geometries. Flow around a long cylinder can be modeled as two-dimensional because variations along the length can be neglected. A bullet is an example of an axisymmetric flow, where the shape and flow are symmetric about an axis. A car represents a complex three-dimensional flow due to its geometry and detailed shape. This classification is important because it determines the analysis approach and model simplifications. By understanding the geometry type, aerodynamic force calculations can be performed more accurately. Check your understanding 1. This section is used to ensure that the concept of two-dimensional flow is well understood. The long cylinder example shows that the flow can be considered identical along the span-wise direction. With this assumption, the analysis becomes much simpler without losing the main physical meaning. This approach is very common in engineering fluid mechanics. Understanding such idealizations is essential in engineering modeling. Impact of streamlining on drag and power efficiency. This comparison shows that the shape of an object strongly affects the power required to move in a fluid. A blunt body needs much more power because it produces high drag. A streamlined body reduces flow separation and the size of the wake behind it. As a result, the drag force is reduced and the required power becomes smaller. This explains why aerodynamic design is so important in modern vehicles. Effects of drag force in high winds. Strong winds generate large drag forces on exposed objects. Trees can bend or even break because of this force. Structures such as power lines or towers can also become unstable due to drag. For humans, these conditions can create safety risks in open areas. This example shows that drag is not only a design issue, but also a safety concern. Forces acting on a two-dimensional body. The forces acting on a body come from pressure and shear stress on its surface. The resultant of all these forces can be decomposed into drag and lift components. Mathematically, lift equals Fr sine phi, and drag equals Fr cos phi. This definition shows that lift and drag are simply projections of the total force. This understanding forms the basis for all subsequent aerodynamic force analyses. Drag force on flat plates, parallel versus normal flow. For flow parallel to a flat plate, the drag force comes only from wall shear stress inside the boundary layer. In this case, there is no pressure difference between the front and back sides of the plate. In contrast, for flow normal to the plate, drag is mainly caused by the pressure difference between the front and rear surfaces. A large wake forms behind the plate and produces dominant pressure drag. This comparison shows that the orientation of a body relative to the flow strongly determines the drag mechanism. Check your understanding. Number 2. This question emphasizes that for flow normal to a flat plate, the primary factor determining drag is the pressure difference. Wall shear stress plays only a minor role compared to pressure effects. This happens because a large wake region forms behind the plate. The pressure in front of the plate is much higher than behind it. This reinforces the concept of pressure drag as the dominant mechanism. Aerodynamic forces on an airplane wing. An airplane wing generates lift because of the pressure difference between the lower and upper surfaces. The airflow also produces a drag force that acts parallel to the flow and opposes the motion. The wing is designed to be streamlined in order to minimize drag and maximize lift. The interaction between the flow and the wing shape determines flight performance. This concept is fundamental in all modern aeronautical design. Terminal velocity in free fall. When an object falls through a fluid, the drag force increases as the velocity increases. At a certain point, the drag force balances the weight minus the buoyant force. At this condition, the net force becomes zero and acceleration stops. The velocity reached at this state is called the terminal velocity. After that, the object continues to move at a constant speed. Drag types and flow around objects. A flat plate parallel to the flow experiences only friction drag and almost no wake formation. A plate normal to the flow produces large pressure drag because of the wide wake region. A cylinder experiences both friction drag and pressure drag, but pressure drag is usually dominant. These differences come from the characteristics of flow separation behind the object. This example shows that shape and orientation strongly influence the type of drag produced. Drag coefficients for streamlined struts. Total drag is a combination of friction drag and pressure drag. The thickness to length ratio, D over L, strongly affects the contribution of each drag component. At small d over L values, friction drag becomes more dominant. At large d over L values, pressure drag dominates because flow separation becomes stronger. This curve shows that there is an optimal shape that minimizes total drag. Check your understanding. Number 3. This question reinforces that at high d over L ratios, pressure drag becomes the dominant mechanism. This happens because thicker shapes trigger earlier flow separation. The separation enlarges the wake and increases the pressure difference. As a result, the contribution of pressure drag becomes much larger than friction drag. This concept is very important in aerodynamic shape design. Drag coefficient of long elliptical cylinders. The drag coefficient decreases as the L over D ratio increases, meaning the shape becomes more streamlined. With a more elongated shape, flow separation can be delayed. This delay reduces the wake size and therefore reduces drag. In the calculation, the reference area used is the frontal area BD. This graph confirms the importance of elongating shapes to reduce drag. Flow separation in a waterfall. Water flowing over a cliff detaches from the surface at a certain point called the separation point. Beyond this point, the flow moves freely and forms a waterfall. This phenomenon is a natural example of boundary layer separation. The sudden change in geometry is the main cause of the separation. This example helps visualize the concept of flow separation in a very clear way. Flow separation over a backward-facing step. When the flow passes over a backward-facing step, it separates from the surface at the step edge. Behind the step, a separated flow region with recirculation is formed. Further downstream, the flow eventually reattaches to the surface at the reattachment point. The length of the separated region is influenced by the boundary layer condition and the step height. This case is often used as a basic model to study flow separation. The airflow around a tennis ball separates from the surface due to its rough texture. This separation forms a wake region behind the ball, characterized by low pressure and turbulent flow. This wake is the main contributor to the drag force acting on the ball. The flow pattern also affects the trajectory of the ball during motion. This example shows the direct relationship between surface condition, flow separation, and aerodynamic forces. Effect of angle of attack on airfoil lift and drag. At a small angle of attack, the flow remains attached to the airfoil surface and produces high lift with low drag. When the angle of attack increases to a moderate value, lift increases, but signs of flow separation start to appear on the upper surface. At a large angle of attack, flow separation becomes dominant and leads to stall. This condition is marked by a drastic reduction in lift and a sharp increase in drag. This phenomenon is very important in defining the safe operating limits of an aircraft. Check your understanding number 4. This question emphasizes that at a large angle of attack, an airfoil experiences stall. Stall occurs because of extensive flow separation on the upper surface of the wing. As a result, the lift force decreases significantly while drag increases sharply. This condition is very dangerous in flight because of the loss of lift. Understanding stall is crucial in aircraft operation and design. Variation of drag coefficient with Reynolds number. At low Reynolds numbers, the drag coefficient fluctuates because the flow is still unsteady. When the Reynolds number increases beyond about 10 to the 4th, the flow becomes fully turbulent and the CD value becomes nearly constant. This change indicates a transition in the flow character around the object. The graph also shows that object geometry affects the response to changes in Reynolds number. This concept is important in aerodynamic modeling and testing. Drag coefficients for different shapes at low Reynolds numbers. At low Reynolds numbers, viscous forces dominate, so the shape of the object strongly affects the drag coefficient. A sphere has CD equals 24 over RE, which is relatively high because of viscous resistance around its surface. A hemisphere has a slightly lower CD due to its smaller frontal area. A circular disk shows different CD values depending on its orientation to the flow. This example shows that in creeping flow, geometry strongly controls flow resistance. Drag coefficients of 2D bodies for RE greater than 10 to the 4th. Objects with sharp corners, such as square rods, have higher drag coefficients than objects with rounded corners. As the L over D ratio increases, CD tends to decrease for streamlined shapes. In turbulent flow, circular and elliptical rods show a significant reduction in CD. This shows that both shape and flow regime influence the magnitude of drag. This table is very useful as a practical reference in engineering design. Representative drag coefficients for 3D bodies. Streamlined bodies have very small drag coefficients compared to blunt objects, such as parachutes or cubes. For ellipsoids and finite cylinders, the CD value decreases as the L/D ratio increases. In addition, the CD value also strongly depends on whether the flow is laminar or turbulent. For a sphere, for example, CD in turbulent flow is much smaller than in laminar flow. This shows that both shape and flow condition are equally important. Check your understanding. Number 5. This question reinforces that increasing the L/D ratio reduces the drag coefficient. Elongating the shape allows the flow to follow the surface contour more easily. As a result, flow separation is delayed and the wake becomes smaller. This directly reduces pressure drag. This concept is a fundamental principle in streamlined shape design. Drag coefficients of various objects and geometries. Drag coefficient values vary widely depending on the shape and configuration of the object. Human posture, bicycle position, and the use of fairings can all significantly change drag. For large vehicles, such as trucks and high-rise buildings, aerodynamic effects are also very important. This example shows that drag reduction can be achieved through simple shape modifications. This principle forms the basis of many modern engineering designs. Impact of orientation on hemisphere drag coefficient. The drag coefficient of a hemisphere strongly depends on its orientation relative to the flow. When the curved side faces the flow, separation is smoother and the drag is relatively low. When the flat side faces the flow, separation occurs earlier and the wake becomes much larger. This increases the pressure difference and causes the drag to rise significantly. This example shows that orientation can be just as important as shape. Birds as models for drag reduction. Birds naturally adopt shapes and postures that minimize drag during flight. By extending the beak forward and folding the feet backward, the frontal area is reduced. This reduction in frontal area directly lowers the drag force. These adaptations are the result of natural optimization over millions of years of evolution. The same principles are widely adopted in modern vehicle and aircraft design. Aerodynamic efficiency of the Toyota Prius. The Toyota Prius has a very low drag coefficient for a passenger car. Its body shape is designed to reduce flow separation and minimize the wake behind the vehicle. This reduction in drag directly contributes to better fuel efficiency. This example shows how aerodynamic principles are applied in commercial products. Such designs are becoming increasingly important in the context of energy-efficient vehicles. Check your understanding. 6. This question reinforces that a small CD value indicates a streamlined and aerodynamically efficient design. A CD value of 0.26 for the Prius means that air resistance is relatively small compared to conventional cars. This explains why the vehicle is more energy efficient at high speeds. Interpreting CD values is very important in evaluating aerodynamic performance. By understanding its meaning, design decisions can be made more rationally. Streamline comparison: classic versus modern car. A classic car shows large flow separation, resulting in a wide wake behind it. A modern car is designed to closely follow potential flow patterns, so separation is much smaller. Although friction effects still exist near the rear, their impact is relatively minor. This difference explains why modern cars are much more aerodynamic. The evolution of vehicle design is strongly influenced by the understanding of fluid mechanics. Drafting effects in cycling. A cyclist riding behind another experiences less drag because they are inside the wake of the leading cyclist. This condition allows significant energy savings. This strategy is widely used in cycling races to improve efficiency and endurance. This phenomenon shows how interactions between bodies in a flow can be exploited. The concepts of wake and low pressure region are the key to the drafting effect. Boundary layer development over a flat plate. Near the plate's surface, the flow starts as laminar and orderly. As the distance from the leading edge increases, the flow enters a transition region and eventually becomes turbulent. The boundary layer thickness grows along the flow direction. In turbulent flow, there are a viscous sublayer, a buffer layer, and an overlap layer. The transition location is determined by the critical Reynolds number. Boundary layer development on a surface. Because of the no-slip condition, the fluid velocity at the surface is 0. The velocity then increases gradually until it reaches about 99% of the free stream velocity. The distance from the surface to this point is defined as the boundary layer thickness. This concept provides a clear operational limit for near-wall flow analysis. Almost all friction effects originate from this thin region. Check your understanding. Number 7. This question reinforces the definition of boundary layer thickness as the location where the velocity reaches 99% of the free stream value. This number is a practical engineering convention that is widely used. With this definition, the boundary layer can be analyzed consistently in many cases. This understanding is important for friction and heat transfer calculations. This simple concept has major implications in engineering. Friction drag in parallel flow over a flat plate. There is no pressure drag because no pressure difference exists between the front and back sides. All the drag force comes from fluid friction with the plate surface. In this condition, the drag coefficient is equal to the friction coefficient, CD equals CF. The magnitude of the drag force is determined by the flow properties and surface condition. This case is a basic model for understanding friction drag. Variation of local friction coefficient over a flat plate. In the laminar region, the local friction coefficient decreases gradually as the boundary layer becomes thicker. When the flow enters the transition region, the friction coefficient increases sharply. In the turbulent region, the value becomes relatively stable but remains higher than in laminar flow. This is caused by stronger momentum mixing in turbulent flow. This graph shows how flow character affects friction force. Average friction coefficient for laminar flat plate flow. The average friction coefficient is obtained by integrating the local coefficient along the plate. For laminar flow, the relation is CF equals 1.328 divided by RE sub L to the 1/2. This equation shows that the friction coefficient decreases as the Reynolds number increases. This means that relatively, friction effects become smaller at higher flow speeds or longer plates. This formula is very important in engineering calculations. Effect of surface roughness on friction coefficient in turbulent flow. On a very smooth surface, the friction coefficient is relatively small. As the relative roughness increases, the friction coefficient also increases significantly. In fully rough conditions, friction becomes much larger because of strong disturbances in the near-wall flow. This shows that surface condition has a strong influence on friction drag. In engineering design, surface quality becomes an important factor. Check your understanding. 8. This question reinforces that in turbulent flow, increasing relative roughness increases the friction coefficient. At certain values, the friction coefficient can reach about 0.0084. This shows how sensitive friction drag is to surface condition. This concept is very relevant for pipes, ship hulls, and aircraft wings. This understanding is important for controlling energy losses. Friction coefficient for flow over smooth and rough plates. At low Reynolds numbers, the flow is laminar and the friction coefficient decreases smoothly as the Reynolds number increases. In the transition region, the behavior of the friction coefficient becomes irregular. In turbulent flow, surface roughness starts to play a very dominant role. Each roughness level has its own curve. This graph combines the effects of Reynolds number and surface roughness at the same time.
Laminar boundary layer separation over a cylinder. At a Reynolds number around 2000, the boundary layer around a cylinder is still laminar when separation occurs. After separation, a turbulent wake forms behind the cylinder. This shows that even if the boundary layer is initially laminar, the wake can become turbulent. This phenomenon is important in understanding the origin of pressure drag on a cylinder. This example also shows the limitation of laminar flow in following surface contours.
Drag coefficient variation for smooth cylinder and sphere. At low Reynolds numbers, viscous forces dominate, so the CD value is very large. As the Reynolds number increases, CD gradually decreases in the laminar region. At the critical Reynolds number, a very sharp drop in CD occurs due to a change in boundary layer behavior. A smooth sphere generally has a smaller CD than a cylinder in turbulent conditions. This graph is very important for understanding the drag crisis phenomenon. Check your understanding, number 9. This question reinforces that at low Reynolds numbers, viscous forces are the main cause of high drag coefficients. In this condition, inertial effects are still small compared to viscous effects. Therefore, the flow is strongly damped by viscosity. This concept is the basis of creeping flow and Stokes flow. This understanding is important for microfluidics and small particle applications. Flow visualization around spheres with and without tripwire. On a smooth sphere, the boundary layer separates early, forming a large wake and producing high drag. By adding a tripwire, the transition to turbulent flow is triggered earlier so that flow separation is delayed. This delay reduces the wake size and significantly lowers drag. This example shows that boundary layer control can be used to reduce drag. The same principle is applied in golf balls and several other engineering applications. Impact of surface roughness on sphere drag coefficient. For a smooth sphere, the drag coefficient remains high until the critical Reynolds number is reached. With a certain amount of roughness, the boundary layer transition to turbulence occurs earlier and drag drops sooner. A golf ball uses this principle with dimples to achieve minimum drag. Each relative roughness value produces a different CD curve. This graph shows that roughness can be strategically used to control drag. Effect of surface roughness and Reynolds number on drag coefficient. At a Reynolds number around 2 × 10⁵, surface roughness can significantly reduce CD compared to a smooth surface. However, at very high Reynolds numbers, roughness can actually increase CD again. This shows that the effect of roughness is not always beneficial under all flow conditions. There is a complex interaction between roughness and flow regime. Therefore, surface design must consider the operating Reynolds number range. Check your understanding. Number 10. This question reinforces that at high Reynolds numbers, a rough surface can produce a higher drag coefficient than at lower Reynolds numbers. The CD value can increase from about 0.1 to about 0.4. This shows that roughness is not always synonymous with drag reduction. Its effect strongly depends on the flow condition. This concept is important in evaluating aerodynamic designs. Key terms for airfoil design. Some important geometric parameters for an airfoil are span, chord, and planform area. The lift force acts perpendicular to the flow direction, while the drag force acts parallel to the flow direction. The angle of attack is defined as the angle between the chord line and the relative airflow direction. These parameters are used in almost all wing aerodynamic analyses. Understanding these basic terms is essential before discussing airfoil performance further. Lift and drag forces on an airfoil. The lift force is the component responsible for raising the aircraft into the air. The drag force is the component that opposes the forward motion of the aircraft. Wall shear stress has very little influence on lift because its direction is almost parallel to the surface. Most of the lift comes from the pressure distribution around the airfoil. This separation helps clarify the role of each force in flight. Flow and lift characteristics for airfoils. In ideal flow, a symmetrical airfoil produces no lift at zero angle of attack because the pressures on both sides are balanced. A non-symmetrical airfoil can also produce zero lift if the stagnation points are balanced. In real flow, a non-symmetrical airfoil generates positive lift because the pressure distribution is not symmetric. The shift of stagnation points is the key to lift generation. This difference shows the importance of considering viscosity and real flow effects. Lift generation through circulation and starting vortex. When the angle of attack is suddenly increased, a starting vortex is formed and shed from the airfoil. At the same time, a circulation develops around the airfoil in the opposite direction. This interaction follows the conservation of angular momentum. This circulation causes a pressure difference and generates lift. This concept is the basis of the Kutta-Joukowski theory. Check your understanding. Number 11. This question reinforces that the starting vortex detaches from the airfoil when the angle of attack is suddenly increased. This detachment is part of the process of establishing circulation around the wing. Without this mechanism, stable lift cannot be generated. This phenomenon shows that the flow is unsteady at the beginning of motion. This understanding is important in the fundamental theory of lift generation. Lift-to-drag ratio, variation for a two-dimensional airfoil. The lift-to-drag ratio increases as the angle of attack increases until it reaches a maximum value. This point represents the most aerodynamically efficient operating condition. Beyond this angle, the ratio drops sharply because stall occurs. In the stall condition, lift decreases and drag increases significantly. Therefore, this ratio is often used as a main indicator of wing efficiency. Effect of flap position on airfoil performance. When the flap is extended, both lift and drag increase, which is very useful for low-speed operations. When the flap is retracted, drag decreases and the aircraft becomes more efficient for cruising flight. During takeoff, the flap is usually partially extended to help generate sufficient lift. During landing, the flap is extended more to allow lower speed and a steeper descent angle. Changing the airfoil shape using the flap modifies the flow pattern around the wing. Effect of flaps on lift and drag coefficients of an airfoil. A clean airfoil shows a linear relationship between lift coefficient and angle of attack up to near stall. By adding a slotted flap, the CL value can be significantly increased for the same angle of attack. A double-slotted flap provides an even greater increase in CL. However, this lift increase is accompanied by an increase in drag coefficient. Therefore, flaps are mainly used for low-speed conditions rather than cruising. Flapped airfoil with slot. The slot functions to direct high-energy flow to the upper surface of the airfoil. This flow helps delay boundary layer separation so that lift remains high at large angles of attack. The flap increases the effective camber of the wing and increases the lift coefficient. The combination of slot and flap provides better flow control. This design is an example of passive boundary layer control. Check your understanding. Number 12. This question reinforces that the main function of the slot is to direct high-energy flow to the upper surface. By doing this, flow separation can be delayed. This delay allows the wing to generate more lift before stall. This concept is very important in the design of commercial aircraft wings. This understanding explains why many aircraft use slotted flap systems. Variation of lift coefficient with angle of attack. A symmetrical airfoil produces no lift at zero angle of attack and shows a linear relationship between CL and angle of attack. A non-symmetrical airfoil can generate lift even at zero angle of attack because of its cambered shape. Both types of airfoils experience a decrease in CL after exceeding the critical angle of attack. This decrease marks the occurrence of stall. This graph shows the basic characteristic differences between the two types of airfoils.
Variation of drag coefficient with angle of attack. At small angles of attack, the drag coefficient remains low and nearly constant. As the angle of attack increases, CD starts to increase significantly. This increase is caused by increased flow separation and induced drag. At large angles of attack, drag rises very sharply. This graph shows the trade-off between lift increase and drag penalty. Visualization of trailing vortices. This visualization shows the formation of strong vortices at the wingtips that extend far downstream. These vortices originate from the pressure difference between the lower and upper surfaces of the wing. In jet aircraft, water vapor condensation can make these vortex patterns visible. Wingtip vortices contribute to induced drag. This phenomenon is very important in flight performance and safety analysis. Energy efficiency in formation flying. Geese fly in a V formation to take advantage of the airflow generated by the wings of the bird in front. By staying in the correct position, each bird experiences less drag and saves energy. The same principle is applied by military aircraft flying in certain formations. The interaction of wake and lift distribution is the key to this efficiency. This example shows how aerodynamics can be used collectively. Check your understanding. Number 13. This question reinforces that the V formation is used to improve fuel efficiency and coordination. By using the flow behind the leader's wings, the following birds or aircraft require less energy. This principle is directly related to reducing effective drag. This effect is very important in long-distance flight. This simple concept has a large impact in real operations. Induced drag reduction. Scavenger birds, such as the bearded vulture, spread their wingtip feathers to reduce wingtip vortices. Gliders and modern aircraft use winglets for the same purpose. By reducing the strength of the vortices, induced drag can be significantly reduced. This improves overall aerodynamic efficiency. This example shows how inspiration from nature is applied in engineering. Lift generation on a rotating cylinder. For a non-rotating cylinder, the potential flow is symmetric and produces no lift. When the cylinder rotates, the velocity distribution around it becomes asymmetric. The side with higher velocity has lower pressure, which results in a lift force. This phenomenon can be explained by Bernoulli's principle and is known as the Magnus effect. This example shows that rotation can be used to generate lift. Lift and drag variation for a rotating sphere. As the rotation rate increases, the lift coefficient rises significantly due to the Magnus effect. The drag coefficient initially decreases, then becomes relatively stable, and finally increases again. This behavior shows a complex interaction between rotation and the main flow. The graph is shown for a Reynolds number of about 6 times 10 to the fourth. This example is important for understanding the behavior of spinning balls in sports and engineering. The Wright brothers' first flight at Kitty Hawk. This event marks the first successful powered and controlled flight by humans. The Wright Flyer used a biplane configuration and a custom-built lightweight engine. This success is a historic milestone in the development of modern aeronautics. This achievement was strongly supported by a fundamental understanding of lift, drag, and flow control. This example shows how theory and experiment come together in engineering. Check your understanding. Number 14. This question reinforces that the lift coefficient increases significantly as the rotation rate of the sphere increases. This increase is a direct manifestation of the Magnus effect. The pressure becomes unbalanced around the rotating sphere. As a result, a larger lift force is generated. This concept is very important in sports such as soccer and tennis. References. This section lists the main sources of figures and materials used in the presentation. The primary reference comes from the book by Chengal and Chimbala on fluid mechanics. This book is one of the standard references in modern fluid mechanics education. Using strong references ensures the accuracy of concepts and illustrations. This is also important for maintaining academic integrity in teaching.